Hello everyone. Today we're going to be looking at inequality notes. Today is going to be all review of what you learned in junior high, but we need to review it before we move on to the Algebra 2 inequalities. So hopefully this should be easy in a review. So first thing is what an inequality is. It just says that two values are not equal to each other. And we have our symbols, and we've used inequalities earlier in the year with things such as domain and range, so these should not be foreign. So we have the less than sign, the greater than sign, less than or equal to, and greater than or equal to. Alright, so if you only have one variable and they're an inequality, we call them one variable inequalities, and usually the only variable is an x. So you're going to solve the inequality as you would usually solve a regular linear equation. So you'd have to get all the x's on one side and all the numbers on the other. One key is that if you divide by a negative number, you must flip that inequality symbol. That's something you must remember. Your solutions will be graphed on a number line. You're going to use those are called boundary points. And another kind of key thing is if you are using a greater than or a less than symbol, then you put an open dot on the number line. If you are using a less than or equal to or greater than or equal to, then you put a closed dot on that number line. Okay, the more sign you have, the more of the dot you have. So since I have a less than and an equal to, I have a closed dot because that's more of the dot. If I don't have the equal to, it's less than a dot, that's why it's open. And then you have to figure out how to shade. Inequalities always get shaded, so you can test a value located on a region on either side of that boundary point, plug that number into the original inequality. A true statement means to shade the region where the test point is located, and a false statement means to shade the region opposite to the test point. You can kind of also, as long as the x is on the left-hand side, you can look at which way the inequality is pointing. A greater than would mean the shading has to go to the left, and less than means the shading has to go to the left, and a greater than means the shading has to go to the right. Again, that only works if the x is on the left-hand side. So here are two examples we have here. I have 6 plus 2x is less than or equal to 12 plus 8x minus 3x. So I'm going to solve for x. So I'm going to add all my like terms first. So add that 8x and minus 3x. I want to get all my x's on one side, all my numbers on the other. So I'm going to choose to get all the x's on the right hand side. That way I can use that trick of which way the inequality is pointing. So I'd subtract 5x from both sides, and then I'd have to subtract the 6 from both sides. That leaves me with negative 3x is less than or equal to 6. I can then divide by a negative 3. And just remember, since I am dividing by a negative number, I would have to switch that inequality to a greater than or equal to. And so I end up with x is greater than or equal to negative 2. You only switch the inequality when you divide by negative. If you divide by positive, the inequality stays the same. So now that my x is on the left-hand side, I would put a solid dot at x equals negative 2, because I have more sign, so I need more dot. And now, since my x is on the left-hand side, I can just say, oh, well, our inequality is pointing to the right, so my shading must be to the right, and that makes sense because I'm saying x is greater than or equal to negative 2, and numbers such as 1, 2, 3, 4, 5 are greater than negative 2. So you have the algebraic solution right here, and you also need a graphic solution with shading. Alright, then we also have what we call compound inequalities, and that's where we have two inequalities and the x is normally in the middle. It looks like a domain or range. So to do that, we're solving for that x using our PEMDAS backwards. So we are going to subtract one first, but now instead of doing it to both sides, we have kind of three sides to do it from, the middle, the left, and the right. So I'll subtract one from all sides first. And then I still have to get that x totally by itself, so I'll divide all sides by 2. and now x is by itself, so I end up with negative 2 is less than or equal to x, which is less than or equal to 4, which really means that x is in between and including negative 2 and 4. It's like looks like a domain. So I put a solid dot at negative 2 and a solid dot at 4, and the shading would have to be in the middle because all those values in between negative 2 and 4 are the ones that need to be included. Try example 2 and 4 on your own. Pause the video, do them, and then move on to the next page. Alright, the next part is graphing two variable linear inequalities. And so here are steps for that. Make sure the inequality is in y equals form. You're not going to have an equal sign, you're going to have an inequality, but make sure the y is by itself. If it is not by itself, you need to undo everything to get the y by itself. You're going to graph the inequality on an xy plane, xy coordinate plane using the slope and the y-intercept. And again, just like we had before, the inequality determines kind of what line you use. So you have less than or greater than sign is a dotted line, and you have a less than or equal to or greater than or equal to is a solid line. But I remember, I think of this little rap. You got less of the sign, you got less of the line. You got more of the sign, you got more of the line. So that's how I remember it. You have more sign here, you got a more line because it's solid. You have less sign here, you have less line because it's dotted. Yeah. If you like the rap, use it. So, once you actually go ahead and graph that using the dotted solid, you still need to shade. And again, you can pick a test point that's not on the line. You plug that test point into the regional inequality. A true statement means to shade the region where the test point is located, and a false statement would mean to shade the region opposite to that test point. Alright, so here's our example. We have y is greater than 2x minus 1, so just using normal linear graphing, we know our slope is 2 over 1, my y-intercept is 0, negative 1. And since I have less sign here, I got less line, according to my rap, right? So, less sign, I need a dotted line, less line. Now, I need my shading. So there are two ways that you can do the shading. You can do the test point way, which I explained above, or you can do what I call the logic way. So again, as long as the y is on the left-hand side, you can do this. So it's saying the y is greater than. So you look at the y values, you look at where the y-intercept is, and you're saying, okay, y needs to be greater. So where are the greater y values? The greater y values need to be shaded. The greater y values are up here, because down here are the lesser y values. So anywhere up in this region needs to be shaded, because these include the greater y values. Now if you don't like that way, you can use the test point way, where you pick a point not on the line. 0, 0 is usually a nice easy one, as long as it's not on the line, which this one's not. So I'm testing 0, 0, put 0 in for x, 0 for y. I get 0 is greater than negative 1, which is a true statement, meaning 0, 0 has to be included in the shaded region. And lo and behold, 0, 0 would be in this part of the line, on this side of the line, so that whole side needs to be shaded. Go ahead and try the second example on your own. Compare them with your group members, and then move on to the next part of the notes. Alright, the last one then is meanings of solutions. So any point in the shaded region is a solution to the inequality. To solve an equation using the graph means to pick a number or point in the shaded region. So if you're doing a graph and they say, give me a solution, you just pick any point on the shaded region of the graph. Now they may also have you do it algebraically. To check to see if a number or point is a solution algebraically, you must substitute the x value in for x and the y value in for y. If it makes a true statement, the ordered pair is a solution. Alright, so here's an example. This is the example for the left-hand side ones above. The y is greater than 2x minus 1. So, it says for the inequalities above, use the graph to state 2 points that are solutions. Remember, if I'm using the graph, I can just go up here, pick any 2 points in that shaded region. It cannot be on a dotted line. It could be on a solid line. Any 2 points in the shaded region will work. So I wrote down negative 2, 1 and 0, 9. Negative 2, 1, clearly in the shaded region. 0, 9, clearly in that shaded region. Solutions using the graph. Also, I can check algebraically to see if something is a point. So algebraically means I have to actually plug them into the equation. So if the point 2, 1 needs to be checked, 2 is my x, 1 is my y. I plug that into my inequality on the left-hand side. And I end up with 1 is greater than 3. 1 is not greater than 3. So therefore, 2, 1 is not a solution. Alright, so there's your review notes. This should all be a review. Then go ahead and complete your homework.